Okay, hi audience and student. So this lecture 8 is talking about the phase margin and converter dynamics or converter performance. In the previous lectures, we used asymptotic analysis to predict or evaluate the closed loop performance of voltage mode controlled converter, and for that cases, the prediction was very accurate. But at that case, the phase margin was sufficiently large, larger than 60 degrees, 67 something. Okay, so for the sufficiently large phase margin, everything is fine. Okay, then the problem is what will happen if phase margin is less than 60 degree or something smaller than that, maybe 15 or less than that. Okay, that can be a question. Right? So to be specific, we use the asymptotic analysis. Basically, this is the exact expression. I'm using the output impedance as an example. So this is the closed loop output impedance expression. This is the open loop output impedance expression or load current to output transfer function. And the denominator is 1 plus Tm. So if the magnitude of the Tm loop gain is larger than unity, we are using this for this, and if the loop gain, magnitude of the loop gain is smaller than unity, we just get rid of this Tm and we are using Gp as the GO expression. Okay, that is the basic approach in the asymptotic analysis. Okay, then question is what will happen if the magnitude of the loop gain is exactly 1? Okay, we have this inequality sign here. Then how about this case? The GOS, output impedance characteristics, when TMS, magnitude of the TM is 1, that is the loop gain crossover frequency in Bode plot, and that is also the unit circle crossing over frequency in polar plot. Okay, maybe this is the one, then you attempt to divide this thing by the 2, but that is not true. Okay, for example, let's consider this case. Okay, magnitude of this is 1. For example, Tm is 1, and but phase of Tm is minus 180 degree. Okay, then this one and this one is out of phase. Then denominator becomes 0, then whole thing becomes infinity. So we have very sharp peaking, infinity peaking, theoretically. Okay, so this is the one extreme example, but we want to know what will happen if phase margin is not sufficiently large enough. Okay, so that is one question. Okay, and another one is this GOS is closely related with the output voltage response due to the step change in the load current. We went through this several times. So this is the S-domain expression of step change in load current, output current. So I step is the size of the step change, and divided by S is S-domain expression of this one. And this is the disturbance source, and this is the closure transfer function. From disturbance source to out voltage, then this will be S-domain expression of out voltage. If you take the inverse Laplace transformation, then you will get the time domain response of out voltage. Okay, so this theory is extremely simple. So let me show 2 examples. I have 2 examples. Okay, one here. This phase margin is 65 degree, so this is sufficiently large. And in this example, phase margin is only 16 degree, so phase margin is small, relatively small, much smaller than 60 degree. So for this case, we are using this asymptotic analysis. Okay, so the borderline between this analysis is this loop gain crossover frequency. After this frequency, the magnitude curve of output impedance is just a copy of this open loop load current to output transfer function. And below these frequencies where the magnitude of loop gain is larger than unity, then you have this rule. Okay, this is the division in linear scale, but in log scale, there is a subtraction of magnitude. So you have a subtraction rule. So the area of this region is the same as this. This represents the additional benefit, additional attenuation of output impedance from this open loop output impedance, this closed loop output impedance due to the presence of feedback control. Okay, this is one of the important reasons using the feedback control. Of course, the most important, most apparent reason is to have our voltage regulated at fixed voltage in the steady state. So that is one, and another one is this one. So this is the simulation result. So this prediction is very accurate. Okay, and with this output impedance, and this is the step load change response of our voltage based on this equation. Later on, you will predict this, and this is the almost the best possible transient response of this converter. So it goes down when this current steps up. Why is that? Our voltage is fixed, and load current is extracting more energy. Then temporarily, our capacitor voltage will be reduced. Okay, so it goes down, and later on, due to the action of the negative feedback, it's recovering. So we have here the undershoot, and for this case, overshoot. Okay, this is almost the optimum response in two sense. This is really the first order system response, just exponential function, and this time, settling time, transition time is very small. Okay, so this is another example, and the phase margin is 60 degree. Then based on this is the open loop load current to output transfer function. This is the output impedance, and from here, maybe in this region, frequencies higher than this vertical line, maybe this approximation is valid. This is valid, and at the frequency below this approximation, it's not an approximation, our definition is valid. Okay, but this frequency, you have some peaking, and around that frequency, there is a deviation between our rule of this. Okay, this is because of the smaller phase margin. When phase margin is more than 60 degree, this asymptotic analysis is very accurate, but with this phase margin is reduced from 65 to 16 degree, there is something else is going on here. Okay, so we want to know what is happening in between this lower frequency bound and this upper frequency bound. In between two frequencies, you want to know the exact characteristic of this output impedance and transient response of our voltage due to step load change. Okay, this is the same response as this one, only this phase margin is reduced like this. Then this is very oscillatory. Okay, and this is very oscillatory, and this undershoot or overshoot is increased a lot, and this time constant, maybe this takes long time to settle into the steady state. Still, converter is stable, but this transient characteristic is very bad compared to the previous one. It shows worse characteristics. Okay, so we want to investigate the details about this. The story behind this is coming next. Okay, that is very interesting. Okay, so this is the general case. In general, our asymptotic analysis method is this closed loop transfer function. Previous case, it was output impedance. Is open loop. Previous case, it was load current to output transfer function divided by 1 plus TMS. And we are using this. We define this. It's not approximation. We have a new definition. When TM, magnitude of the loop gain, is larger than unity, we take this. Otherwise, we take this. Okay. So this is good. If the frequency range where this TM is much larger than 1, this is good. And this is also good when magnitude of TM is much smaller than unity. That is good. Then what about in the neighborhood of loop gain crossover frequency? by definition, the magnitude of the loop gain is 1 at the loop gain crossover frequency, and around that frequency region, loop gain magnitude is very small, okay, larger than 1, but slightly larger than 1, and smaller than 1, but slightly smaller than 1, then there should be some problem, accuracy problem. So we want to investigate that. So to predict that, the method we have taken is we analyze at the loop gain crossover frequency. Okay? So in-depth analysis is advanced analysis will be done. So I showed this. In the previous, maybe I'm showing this. Okay, this is the Bode plot of the some loop gain. So this is magnitude. Okay, this is the loop gain crossover frequency. So magnitude of this loop gain becomes 1, and it becomes 0 dB in log scale. Okay, and the same information is shown here when this magnitude of the loop gain becomes 1. That polar plot trajectory crosses the unit circle because the radius from origin to this unit circle is 1. Okay, so at that frequency, you define the phase margin. Phase margin is margin at this frequency, loop gain crossover frequency, and difference between minus 180 degree. So this is defined as phase margin. So this is the formal definition of the phase margin. So here, phase margin is larger than 1. Larger than 0. So you have a positive phase margin. So converter is stable. Think about the Nyquist stability criterion. Okay, that comes from that. And there are many ways of explaining this. Okay, and this one, phase is exactly minus 180 degree. Then phase margin is 0. So this 0 is becomes marginally stable system, and the marginally stable system is generating oscillation. So we don't want this, okay? When you are designing the converter, you want to have output fixed at the desired value. So this is oscillating, output will be something like this. So this can be considered as unstable, undesirable. Finally, for this case, phase is lower than minus 180 degree, and phase margin becomes negative number. It's unstable. So if you project this one to the polar plot, the first is this one. This is omega c. At the omega c, gain crossover frequency. This should be omega c is here. At the omega c, the phase, at this phase, this one, phase Tm, and this is a minus 180 degree. The difference between two line segments is defined as a phase margin, which is positive in this case. And for this case, the same line, so phase margin is 0. And for this case, phase margin becomes negative. Okay, so this is the same graph. It carries the same information. One is in Bode plot format. So here we have two graphs, magnitude and the phase. Advantage of this is the frequency is explicitly shown in this graph. Okay, we are using only one graph, and the information about the phase and magnitude are shown all together, but frequency information is shown here. Okay, so you need something else, some other information to figure out this frequency at this particular point, but eventually, effectively, they carry the same information. Okay, so this is the trajectory. It's called the trajectory. So I copied the trajectory here. Let me say one thing. Okay, so this is the phase margin is positive. That means the phase is less negative than minus 180 degree. Then phase margin is positive. So in this region, phase margin is positive, and phase margin here, this phase margin is more negative than minus 180 degree. Then the phase margin becomes negative. Okay, so this is unstable region. If you have something like this, they are all unstable. If you see something like this, they are all stable. Okay, so we are dealing with the minus sign. Okay, but you don't you don't need to confuse with that. Okay, the concept is very simple here. All right. Okay, this is the same graph as shown here. So I copied this polar plot trajectory to here. So this is the polar plot trajectory, and now we define phase margin as pi m. Okay, so pi m is the phase margin. This was the polar plot trajectory we have seen in the previous lecture slide. Okay, we take a snapshot here. Okay, so to investigate the nature of the phase margin more closely or more accurately or more informatively, consider the snapshot. Okay, so this is passing this point, then you take a picture of this vector. When it passes here, you take the picture of this here. When this passes this point, you take the picture. Okay, so this is a snapshot. It's the fixed vector, not moving, because this is a snapshot. They are frozen in frequency. Okay, so then you see this one is stable, because when this trajectory is passing through this unit circle, phase is less negative than minus 180 degree, and difference between phase at this frequency and this minus 180 is defined as phase margin. So we are using new notation pi m. So pi m is positive. Okay, so here pi m is 0, and at this point pi m is 180 degree. So this is the stable region. Okay, as I said in the previous lecture slide, if the snapshot occurs in this region, that means phase at the unit circle crossing over frequency. Phase is more negative than minus 180 degree, then system is unstable. Okay, so this is the unstable. All right, but phase is the same. The absolute value of the phase margin is the same. This is plus 1 and this is negative 1. They are symmetrical. Okay, so all right, so drawing this is to understand the nature of the phase margin more clearly. So I have another figure shown here. Okay, so this is just a half circle. I take out this part and I'm showing only this lower part, lower half circle, as shown here, which is this one. Okay, so we have this relationship. This is the exact relationship. There is no approximation or anything. This is the exact expression. And here, suppose we know this and we want to evaluate this, then we need to know this guy, magnitude of the 1 plus Tm, evaluation of 1 plus Tm, but this is the vector. This is the complex number, so it has magnitude and phase, so they are vectors. Okay, so this is the vector length at loop gain crossover frequency, and by definition, at loop gain crossover frequency, magnitude of this loop gain is unity. Okay, so that one example is shown here. So we are trying to evaluate this sum of two vector lengths. One vector is this one. This is 1, 0 vector, one vector, and this is the loop gain. This is loop gain. Length of the loop gain is 1. Okay, this is a unit circle. This is the definition of crossover frequency. So at the crossover frequency, its length is 1. Okay, we are trying to evaluate this vector summation of this, and we have the parallel diagram rule for the vector addition. Then resulting vector is this one, this purple color one. Okay, so we desire to derive the equation for this length. Okay, that's very simple. All right. So here, this is minus 180 degree, and this is the phase of loop gain at 0 dB crossover frequency, and this is the difference between them is the what? This is the phase margin. This is the definition of a phase margin, pi m. This is the phase margin here. Okay, and this is the one, and you move this parallelly, then you have the same thing here. And you move down here. This is a parallelogram. So length of everything is, this is 1, this is 1, this will be 1, and this will be 1. Okay? And this angle, they are corresponding angles. They are the same in Korean. 동의각. Okay? So they are the same angle. And you evaluate this. Okay? Then this length is 1. So this length is 1. Then this length is cosine pi m. This length is sine pi m. This is cosine pi m. And this length is 1. So this length is 1 minus this one, cosine pi m. And this is sine pi m. And this is sine pi m. Okay, this and this should be the same. Okay, no. This and this is the sine pi m. Then you evaluate, this is sine pi m. And this is 1 minus cosine pi m. This is the right angle, triangle. So you have Pythagorean formula. And using that formula, you evaluate this. And using the trigonometric function rule, this is the simplified version of it. Okay? So this is actually the length of the Tm vector from the origin. Okay? This represents just this length. All right? So then, at the crossover frequency, magnitude of closed loop transfer function is open loop transfer function divided by 1 plus Tm, and this one. Okay, we separate. Okay, in log scale, it becomes addition. So, if you write down this manner, this is the open loop magnitude of open loop transfer function, and this can be peaking or dipping. If this is the larger than 1, 0 dB, then becomes peaking. If this is the smaller than 0 dB, negative dB, it becomes dipping. Okay? So assume this is a peaking and the magnitude of peaking. If it generates peaking, that becomes this one, and this is the equation. Okay? And this equation, this denominator, is actually length of this. Okay? Length from origin to this. Okay? Loop gain. No. This is unit circle crossover frequency of loop gain. All right? Okay. So this is a very general formula. Okay? This is very easy to derive. Okay? I derived this somehow during some process. I don't know. Maybe somebody else derived the same thing, but I don't know. I don't care. And this is the example. So looks complicated, but this is not difficult to chart. Okay, slide itself is very simple. Okay, consider this one. So this is the one vector, and this is Tm loop gain. This phase margin is difference between this and this is 30 degree. Okay, then the addition of this one becomes this one. Okay. Length of this is obviously smaller than this one. Okay? Then denominator becomes smaller than unity. Then the peaking is 1 divided by denominator. So peaking becomes positive. Okay? So it will generate, because this is smaller than unity, it will generate peaking. Okay? When the phase margin is 60 degree, so this is 60 degree, then you have this triangle. And this triangle and this triangle are the same. They are unilateral triangles. In Korean, 정삼각형. Okay? So everything is same. The unit is 1. The length is 1. Then we don't have any peaking because the denominator becomes 1 because the length is 1. Length is smaller than unity. Okay? Or you can evaluate this numerically. Okay. So this is 0 dB, all right? And this is some positive dB, okay? Let's consider this phase margin is 90 degree. Then 90 degree is something like this, okay? 90 degrees. The resulting vector is this, okay? This is the larger than unity. Then this one divided by something larger than unity becomes smaller than unity, so you have this minus 3 dB. Peaking, okay? So negative peaking means dipping. Actually, there is a dipping, okay? So here is a case. For this case, with this 30-degree phase margin, you can evaluate length or you calculate this. Then there is a 5.7 dB peaking, okay? And in here, with the 60-degree phase margin, there is no peaking. And in this one, with the 90-degree phase margin, this is the dipping. Maybe this should be 3 dB. Depth should be 3 dB, okay? This is for the positive case. No. Stable case. This is a stable case, okay? When there is a polar plot of loop gain, snapshot is here, then length sum of this and this is 0, okay? They have same length but out of phase, okay? So 0, so there is infinity peaking, right? So when this phase margin is large, then there is no peaking. Smaller phase margin, we have some peaking. With 0 phase margin, you have infinity peaking. With negative phase margin, you have infinity times infinity peaking. That is not true. Okay, this is a symmetric. So peaking will reduce and eventually disappear, and eventually it becomes dipping. But still, this converter is unstable. So you should consider something else. Okay. So I have it drawn here. This is the root trajectory, okay, conceptual root trajectory. This is different from this plot, okay. This axis is the same. This is in complex plane. When phase margin is 0, so then this pole, one pole occurs here, okay. At the imaginary axis, Q is infinity, right? So infinity peaking, okay. And this one is slightly right-hand side of this. Then phase margin is negative, very small, but still negative, 0 minus. And this one, phase margin is very small, but still positive. So this one is stable one. This is the oscillatory one. This is unstable one. Okay. So this is the way of understanding this in terms of the root locus. So maybe you can use root locus in some cases. They are same thing. Bode plot, polar plot, root locus, they are all the same thing. Okay. In the classical control theory, they are playing with the same thing in different manner to confuse people, to confuse students, and they bring something else unnecessary to confuse you further. Okay. So knowing this is very important. So this is stable region, in this region, and remember this is symmetrical, okay? The peaking will be reduced, and the peaking will become dipping in the same manner as this stable case, but if you evaluate the transfer function, characteristic equation of this system, there is one pole here, another pole here in the complex conjugate manner, okay? So this is a story about the phase margin, okay? All right, this is the one case. This is our converter case, okay? We have good design, and I intentionally modified that design to have very small phase margin at this crossover frequency. So phase margin is 16 dB. Then this rule is predicting this dB. This is actually the length of the vector from the origin to the end of loop gain crossing this unit circle, okay? Think about this is the length, okay? Then peaking, as this one, this peaking, okay? So when you are evaluating peaking, you should consider the maximum value and this value of open loop transfer function, not this one. This one, this is almost 11 dB, okay? So peaking as this one, 20 log, this one, okay? This is one story. Another story is in the network theory or electronics, you learn at this frequency, there is a peaking of 20 log Q. Q is quality factor of the circuit, so they are same thing, okay? So this can be used as the approximation of the Q in many times. So this whole thing becomes Q. Okay? So because this one equation we derived from the geometry of this thing, there is another equation derived from the Bode plot characteristic of this. But so this is same, then this inside of the this logarithm must be same as Q. Okay? So you know this, you know the peaking, but if you know the peaking, there is a relationship between this peaking and this bandwidth. Okay? Bandwidth is defined as this the peak value of this, and bandwidth of this is the bandwidth of the frequency where this the magnitude of this value decrease by 3 dB from this top value. Okay? So there is this equation. So omega naught is resonant frequency divided by 2 pi divided by Q is this one. Then this will be determined. Okay? You have high Q. This is very narrow. This is very peaky. You know the word peaky. Okay? But this is smaller than infinity, so it's spread out. Okay? So this predicts not only this peak value, so behavior of this plot around this frequency range. Okay? So you are using the older theory about the linear time invariant system. Okay? So why is that? Because we derived the small signal model of a converter. Everything is based on the small signal model. So you can use whatever knowledge you obtained from your undergraduate course. Right? That is very important. Okay? That is actually the only purpose of the modeling, deriving small signal model. Okay? You are not interested in very small thing about that. Our only interest is to use the existing knowledge about linear time invariant system. Okay? So you can predict this peak. Also, you can predict the behavior of these things around this region using this, and you smoothly connect this one. Then you will obtain the closed loop shape or magnitude curve of closed loop of impedance. Okay, that is the story. I have another example here, but same example, but more detailed explanation about the output impedance and its relationship to the step load response. Okay, so this is the equation. This is the example. So this is the same as previous one. This pi m prime is output impedance with 16 degree phase margin, and this pi m prime is 16 degree phase margin, and the pi m is 65 degree phase margin. So this is the with small signal, small phase margin, and this is the original design, which is the best possible design. Okay, for that case is this one. So this one, then maybe you plot with this red curve. Red curve is this one. This omega p. All right. So it is first order system. This is a differentiation, and there's one pole, and you consider this is the horizontal line. Okay. Then you write down this. Okay. This is this is a differentiation, and there is one pole. Okay. Problem is to evaluate this. There are two different ways of evaluating this. One is you extend this line segment, and this 0 dB line at the crossing over frequency is Km. Okay. So this value, if you read this as 1000 and Km is 1000, because with this, when this omega is 1000, this becomes 1. This is 0 dB. Okay, that is one way of evaluating this Km. This Km. Another way is consider this at very high frequency. So this S is approaching to the infinity. Then you take only coefficient. So Km is here, and omega p is going upstairs, and this one is the same as this one. At high frequencies, the output impedance is same as RC, ESR of our capacitor, regardless of the presence of the feedback loop. Okay, that is true for the open loop case and the closed loop case. And by equating this, you find out this. Okay, it really doesn't matter. So this is the expression of this best design, and this is this shape is this output impedance of this smaller phase margin with the smaller phase margin, so it has peaking. Okay, so this is the equation, right? So if you have peaking means peaking is the second order behavior. So there is a second order behavior in the transfer function that will generate oscillation. Okay, so here we have underdamped second order term in GOS, then decaying. The sinusoidal term will be contained in the voltage. Okay, so we are not doing anything, just this from this the common knowledge of linear time invariant system, we are expecting this oscillation will occur like this. Okay, all right. If you want to know the exact equation of this, that's very easy. Okay, so this one, this with a small phase margin, so you have this. Okay, then this omega p, this line segment is the same as the previous case. So S divided Km is here, and here you have this omega p here, and you have double pole here. Okay, because slope is +1 and slope is -1, so there is this second order term, and this omega c, this is the peaking occurs at the loop gain crossover frequency. So this omega c is loop gain crossover frequency, and this magnitude is 20 log Q. So from this magnitude, you can predict this, or okay, you can use either way. We have some formula. Okay, this is the same. This is the same as this one, but just from the magnitude, then you know everything, and there is a ESR 0, then ES 0, and you multiply this with, for the step change, I step divided by S, SS cancel, and you take the inverse Laplace transformation of this, then you will obtain equation of this. Okay, so doing this is nothing. Okay, is piece of cake. Okay, just simple algebra. Okay, but the idea is important. Okay, so evaluating this is not important, but if you want, you can evaluate that. All right, but anyway, this omega c is generating this oscillation, and oscillation frequency can be predict this frequency, which is what? Loop gain crossover frequency. Okay, so oscillation frequency is this one. Oscillation TOS, oscillation period, is 2 pi divided by omega c, and it is calculated as this one, and this is this peak, then maybe this is very similar to this number. Okay, and with this you can evaluate this time. Right? But it's unnecessary. Okay, this is simple algebra. Okay, and here this is the first order system. If you assume you do same thing, then you will have one exponential term, and this time constant of this exponential term is determined by this omega p. So maybe settling time is 3 times of this. Okay, this time constant tau. Okay, let me. If I touch this, that will happen again. Be very careful with it. This tau. Okay. All right. So you can predict most of transient behavior of this PWM converter, and actually this response of this is something similar to this. And okay, this is okay. All right. So we started from here. We come back this steady state. Okay, but during this transition period, the response becomes very wild. Okay. Nobody will prefer that. Okay. Right. So the conclusion, the message from this analysis is loop gain is not simply phase margin is not simply margin in the phase delay. Okay, the phase margin can be used as the index or barometer how your design is good, how your converter performs well is determined by the phase margin. Okay, so there is a rule. So this is called the rule of thumb. Okay, so phase margin in between 45 to 70 degree is recommended by many people. Okay, what will happen if you go to higher than this? Then you are sacrificing something else. Okay? There's no free lunch in the world. So if you obtain something extra, you should pay something. Okay? So this is the good trade-off between 60 degree, 45 to 70 degree. Maybe 60 degree is a good number. Okay? So this is the guideline. Okay? Because this phase margin can be used as the barometer of your compensation design and the closed-loop performance of your converter. Okay? Another important thing is consider this one. This is the loop gain plot, asymptotic plot. The phase of this is -2, and there is a 1, 0. So phase changed to this minus 1 slope, and there is double pole here. So phase becomes -1, -3. Okay? So maybe you think this is good because you have good phase margin here. Okay? So this was -2. Slope is -180 degree, and with this phase will increase toward -90 degree, but in the middle you have the point of this one, so you have a 60 degree of the phase margin. Okay? But if the crossover frequency changes to this direction, phase margin will be reduced. Okay? But then might be okay. But if the crossover frequency changes this direction, here we have double pole here, then phase margin is dropping from here to there to this degree. Okay? Then if your crossover is increased a little bit, or you miscalculate your crossover frequency, the actual phase is very bad. Okay? Can be unstable. Right? So not only this number is important, not only this number alone is important, but also this this slope around this crossover frequency is very important. Okay, so the loop gain crossover frequency, this phase should not change abruptly. Okay, so if you maintain this minus slope for the wider frequency range, then you have very stable phase margin. It won't change much regardless of miscalculation in the crossover frequency. Understand this? Okay. All right, so this is end of this lecture. Again, I'd like to emphasize the importance and implication of the phase margin. Phase margin is not simply some margin or something. It indicates the goodness of your control design and the performance of your converter. Okay.